Good morning or afternoon, everyone. Welcome to our live demo webinar focusing on how to automate RNA prep with enrichment on the Opentrons Flex. I'm Nick Rizzo. I'm a product manager here at Opentrons, and I'm joined by my colleague Matt Akana, a senior NGS scientist here at Opentrons. Today, we're going to talk through automating Illumina RNA prep with enrichment and how the Opentrons Flex high-throughput NGS workstation sets you up for success with this longer and more complicated genomics application. In particular, we're going to cover how you can use the brand new Flex stackers, which you can see over to my side here, to really easily scale this workflow while working within the Opentrons ecosystem. And we're also going to highlight the use of our new low volume 96-channel pipette, as well as some of the other on-deck modules that you'll need for this workflow, whether that's the thermocycler, heater shaker, or magnetic block. We're going to actually start with kind of an overview of the application, and then we're going to run through the hardware with a kind of a live demo there, including kind of like what tips and tricks were used to automate this protocol, and then more specifically, what the hardware is doing to help us accomplish those goals. I'm just going to pause here for a minute to make sure everyone who signed up can join us. And I'll also use this time to plug our demo room, which is where this webinar is taking place. This demo room is in our headquarters, which is in Long Island City, New York. If you or anyone else from your team are based out of or are visiting New York or the broader tri-state area, please feel free to work with our team here at Opentrons to schedule a time to come and visit. Check out our office and lab, get to see some of our friendly faces and the Opentrons Flex in person. Okay, looks like we're probably just about ready to go. So just a quick reminder to everyone that this webinar is being recorded and it will be made available on the Opentrons website. We'll also be sending a copy of the recording via email to everyone who registered after the webinar. To help with the overall webinar experience, all attendees are on mute. To ask a question, please use the Q&A box on the bottom of your screen, and we'll answer all of your questions at the end after Matt and myself have already presented. Okay, great. Let's get started. So the first thing that we'll do is I'll hand it over to my colleague Matt to talk about how the Flex supports kind of the long and complicated protocols like RNA prep with enrichment, as well as talking, kind of more in detail about how protocols like this, might be looking at 10 or more hours of kind of manual lab work, plus hybridization times, which might be overnight or longer, adding up to kind of, maybe a day and a half worth of actual workload here. So there's obviously huge benefit to automating these workflows. And there's also challenges in terms of tip management, preventing contamination, and also just the commitment to creating and also optimizing these protocols. So I'll hand it over to Matt here, who can go through some of the tips and tricks that they've used in order to kind of enable this protocol. Okay, perfect. Matt, here you go.
All right, thank you. Thank you, sir. I'm all mic'd up. Hear me? Thank you for the wonderful introduction. I'll jump into my slides in a second. But yeah, just to introduce myself, my name is Matt. I'm one of the science guys here. I work on the bench, and my job primarily is to write script protocols to use on the Flex and sort of demonstrate how a robot like this can help me in my library prep. Right, so I believe you're looking at my screen right now, so I have a few slides sort of to go over what I'll be talking about. So once we got the Flex and we got all these new tools to sort of increase the usability of the robot, we were thinking, what is the longest, largest protocol we could put onto it to sort of demonstrate how well it could work? So you see in the center, previously what we started with is just the Illumina DNA prep. This is, for those who are unfamiliar, this is just Illumina's basic tagmentation. So the tagmentation is using a bead transposon to simultaneously tag and frag your DNA molecules simultaneously. So this sort of chops up your DNA molecules and adds like a little bit of DNA adapter so that you can attach your barcodes to it. So once you go through the entire blue series of steps, you would have a whole genome library that you could put and get sequenced on an Illumina-based sequencer. So all that was well and good. We had that running on the Flex using a 96 channel. Our approach for this was to use a 384 well plate to hold the reagents, both the room temperature stuff and the stuff at 4 degrees. So when using the 96 head for this was a simple, almost plate stamping, and just a direct transfer of 96 samples from the reagent plate to the sample plate. That worked fine. This is back when we had the Flex with a few of the off-deck sort of expansions. So now we have the stackers as well as a few other goodies that we'll cover in a second. So how can we sort of use these things to increase the complexity of the protocols that we're putting on the Flex? So we're going with RNA prep with enrichment. So you see in the first half, we're going to be starting with RNA, which is a lot more finicky. You get maybe it's a lot more sensitive inputs. And then we're going in the last half, we're going to be doing an enrichment. So we're going to be fishing out the desired molecules that we want to actually sequence using an enrichment capture. So we have the red section in front, in which it's the reverse transcription. And then we have the stuff at the end, in which the samples are pooled together. We set it up for hybridization. It hives for a very long period of time. We capture it, and we wash it, and then we do another amplification of it. So if you look at this entire protocol, we can sort of break it up into multiple steps. And we have 3 different beads being used in this protocol. We have the tagmentation beads, we have the regular cleanup beads, and at the end, during the capture washes, we have the streptavidin beads. So all these different steps have different sort of requirements that had to be sort of finessed and fine-tuned. And also the scale changes. As we go through the red and the blue sections, we're dealing with each sample independently. It's still in a 96 well format. But after the pooling by volume, the scale of the amount of samples you're handling, the throughput sort of reduces. If you're doing the RNA prep, which we were doing, everything is pooled by 3. So you go from 96 samples down to 32 pools, which is 4 columns. Or if you're doing, let's say, Illumina's exome capture, that is, I believe the suggested is pooled by 12. So you go from a 96, the 12 columns, you get pulled down to a single column. So this adds the additional complexity of using the 96 channel head to sort of handle these different sample throughputs at various stages throughout the protocol. So this is my approach to how I put this protocol on our robot. It mostly depends, since this is such a long and complex protocol, it depends on what is your sort of goal for automating this. Mine was to automate this so it is mostly, as much as I can, hands-off. So I didn't have to touch the robot. I didn't have to add any additional labware. I didn't have to make any manual moves. If you so desired, you could design this to be semi-automated. Pretty much the reagents are just stamped from reagent plate to the sample plate and just focus primarily automation on just the cleanup steps with the beads, the tedious sort of repetitive washes you can automate, and anything more tricky such as pooling or the hybridization, just handle that manually as sort of up to the user. I mean, that's why we call this the Flex. So in this particular case, I was desired to hybridize this overnight. If you see down in the little column, you can hybridize the suggested like 90 minutes to 24 hours. I could be ambitious and try to squeeze this all into one very long day, but I decided 16 hours overnight in an off-deck hive oven is fine. I didn't want to tie up our robot to be doing a thermocycler incubation overnight, so I just had a pause to put that in a off-deck thermocycler. I also had a pause for the QC. When I do this when you would do this manually, you would go through the RNA RT step, you would go through the regular DNA tagmentation step, and then you would pause and you would quantify and sort of check your samples and then balance them so that your pools have like equal amounts of each sample's mass. If we're pooling by 3 samples, you would have 200 nanograms of sample per sample and 3 samples per pool. In this particular case, I've lead everything on the robot. I would take my sample, I would pause the protocol, I would go quantify it and dilute the samples if necessary, if any of the samples seemed a little too high. Um, that's why, yeah, for amplification, you see I have it for 17 cycles. And then the hybridization, in this case, we are using Illumina's RVOP, the respiratory virus oligo panel number 2. This is the one that I was familiar. I first started off with back in 2021 with the whole COVID pandemic. Because in this particular case, we would use like 10 nanograms of human input RNA. We would spike in a known amount of virus control. I believe it was the COVID control from Twist. We would spike that into the sample and go through the enrichment capture using RVOP. And then since Illumina sort of developed the pipeline on base space, they have a whole analysis software to sort of detect the levels of COVID in your sample. So if I have a breakdown of in blue of roughly the amount of time per step. So I could do this like manually. This automation is still going to take, as you see, the first section is an 8-hour day, followed by overnight, and then another 3 hours on the last day to do the capture wash. This is not necessarily faster, but most importantly, it frees up the user. I can walk away. In this particular case, I come back, I check just the QC step. That was my main goal in this particular protocol, was hands off. All right, so now you're looking at the deck setup. So now we have, you see on the furthest right, we have the stackers represented here as sort of like that gray rectangle expanding from the 4th column to a new 5th column. So the stacker, as you'll see in a few moments, has the shuttle that could retrieve whatever stab library there is and put it into that 4th position. So overall, in this entire protocol, I'm using about 12 P200 tip racks, 12 P50 tip racks, 7 PCR plates, that's including the Illumina barcode plate that's on the deck, 10 deep well plates to hold all the various washes for the 3 different bead cleanup types, as well as 5 disposable PCR lids. That's the stuff in orange that would go onto the PCR plate as the thermocycler opens and closes. I have 5 of them so I could dispose of them as needed throughout the protocol. And then in that gray box down there is the trash chute. So we would use a tip rack and then the gripper would dump it into the trash chute, clearing up space on the deck. So here is a picture of that previous setup, so what it looks like in real life. The importance here is that you can see the sort of the topography of the decks or the height of the different labwares. Because as I mentioned before, the different steps of the protocol has different pipetting requirements. Sometimes it's column pipetting, sometimes it's even single tip pipetting, which the 96 channel can do. And because of that, the 96 channel, as you'll see, is like a big block. It's not articulated, and all 96 channels go at once, so that the 96 channel head, when it does a single column pickup, will have an overhang into the adjacent positions. In this particular case, you see the sort of silver tip rack adapter in the very back. That's for when it's picking up an entire set of 96 tips. But the 2 tip racks in the center, I have an overhang over the leftmost column where the thermocycler is, so that the 96 channel can pick up just a single column, so I could just do a single dispense. That is sort of the trickle-down effect of having all these different steps put onto the deck at once. I have only one position, the temp module that'll keep things at 4 degrees. So I have about like 10 different reagents that'll have to be kept at 4 degrees. So I have to put them sort of deliberately on the temp module in certain rows. I can only access that one column at a time, hence the single column tip pickup. Not seen here. I also have reagents at room temperature. I have the beads. I have the wash buffers. Those are sitting in a deep well, and those deep wells are sitting right now in one of the stackers. So also in this particular case, I'm pulling by 3 samples at once to do a single pool. So that means from 96 columns, 96 samples, I go down to 4 columns. So once I reach that last third of the protocol in which I'm doing just the capture washes, I'm only dealing with 4 columns at once. And the panel, when doing the hide capture, that for me is sort of like one of the most precious reagents. I have that in a single well, and when I start setting up my hide mixes to do the overnight capture, I use single tip pickup. So that's why I need all the extra space to do a single tip pickup. It uses just the corner channel of the 96 block. That's why I need the additional space to the left and to the bottom so that the overhang doesn't collide with any of the labware. So this was figured out slowly by all sorts of optimizations and slowly testing it to find out what is sort of the best setup of the depth. So if you remember the overall workflow, the first third of the protocol is the cDNA reverse transcription. Most of that is done with a P50. So if you see on the deck, as I use those P50s, 96 samples, 96 tips for each enzyme reaction, I would be dumping those tip racks into the trash chute, clearing up space so I could do the bead washes. So here is sort of a picture. I had 4 stackers going at once. What we're trying to stick with is a single labware type per stacker. So I have 2 of them filled with my P200s, one of them with my P50s, and the last one with all my deep wells. So here's sort of a breakdown in order of what each of those deep wells have in them. So the stackers is able to both sort of dispense a labware and also it could store a labware. So what I kind of did here was that you see the bottom 5, as soon as it's done with all the enzymatic steps of the reverse transcription is ready for cleanup before the tagmentation, I would dispense those 5 different deep wells that have like the cleanup wells, the beads, space for liquid waste, ethanol, and the resuspension buffer. I would dispense all 5 of those, use them, and the blue ones that I highlighted, I'm actually going to save and store back into the stacker. So this is sort of, I believe the term is like pop and restore. I could dispense a bunch of stuff, get, let's say, deep well number 6 that has the actual tag mix and tag stop, and then store back in again the RSB and the cleanup beads that I could use in later steps. This is what I was trying to do to minimize the amount of labware. But actually, if you look closely at the picture over there, I don't think actually it was necessary. I stuck with it, but turns out I have a lot more space. I have space for 5 more deep wells, so I don't even need to store all that labware back again. But it's like, hey, extra space is always good. And here, so we've gone through the reverse transcription, we've gone through the tagmentation, the regular library prep, everything's barcoded. The samples are sort of pooled, they are put into the overnight hide, and now it's ready for the capture wash. So in the enrichment procedure, sort of the capture wash is the most crucial step. It's going to go through 4 heated washes of this enhanced enrichment wash, which is washing away all the off-target molecules. What's happened before early on in my career, in which I go through manually a whole enrichment capture, looks like I have decent yield. I put it on the sequencer, the sequence is fine, the QC is very nice, but the bioinformatics people get back to me that the on-target rate actually is incredibly low. It stinks. It's almost as if I hadn't gone through all the enrichment at all. So the capture washes is sort of like the most critical that you want to make certain like you get right. Otherwise, you won't find out for a long time. So if your temperature is too high, the capturing is going to be a little too stringent. Only the strongest, like perfectly matched target molecules will stick, and everything else will get washed away. And when you go through that last amplification, your yield is going to be very low. You'll have just a smidgen of library. And if you have the temperature too low, it's not actually going to be stringent enough. You're going to have non-specific stuff sticking to the capture beads. And once you actually get back into the sequencer, you're going to find you're going to have a lot of off-target molecules that essentially you're wasting, your sequencing is not very efficient. So it's important to get that temperature just right. In our particular case, the written temperature suggestion is 58 degrees. Here I bumped it up to 59 degrees due to having these in open wells. So what I've done manually before, this whole enrichment capture is done in 1.5 mil tubes. I'm flipping open and close the caps. I'm standing next to a high block and a magnet plate going through each 1.5 mil tube doing the capture wash, 4 washes at a time, times how many tubes. In this particular case, we are now using a deep well block, a deep well plate. It is open to the air, so we bump up the temperature slightly. In our test, we did 59 degrees just to account for that open air, any like loss of temperature. So in this particular case, we have two heating elements on the deck. We have to keep both the samples at 59 degrees as well as that enrichment wash buffer. If that drops or the other drops, you start to get off-target stuff. So we have one element, the thermocycler, still running at 59 degrees, keeping the wash warm. And we have at the bottom, you see the heater shaker, which both keeps the samples at 59 degrees as well as shaking them. So the shaking, as you see the arrow going between the shaker as well as the mag block, so you could sort of bind the beads and remove the supername. Going back and forth, back and forth. I had did this before with the OT2 and without a gripper, manually switching the stuff there and back and forth again. Just all the features now added on the Flex greatly alleviates these things. It's not necessarily faster than I do it manually, but simply being hands-off is a huge value added. A particular note is in the case of using the RNA, since I'm pooling by 3 samples, I have 4 columns. I'm not doing the enrichment washes 1 column at a time. I'm still using 96 tips at once to do the capture washes, even though there's only 4 columns, because I wanted each pool to be treated evenly. I didn't want any delay from the first column to the last column. All right, and here are some results, just a brief sort of synopsis of some of the data that we got for it. Just to recap, in this protocol that I set up, I put in 10 nanograms of human RNA, 1 million copies of spiked-in SARS-CoV from the control from Twist. These are being pooled 3 at a time. This is 200 nanograms of sample pooled, and this is against RVOP2, the respiratory virus oligopanel number 2 from Illumina. The pre-enriched yield, meaning sort of like the basic library prep after the tagmentation, is about 175 nanograms per microliter. CV is about 20%. This in particular case is 17 cycles of amplification. What you kind of want is high enough that you could just pool the samples and maybe dilute it out. What I really wanted to avoid was having a low yield so that I would have to do a vacuum concentration of the samples. So in this particular case, I'm fine sort of having a very high yield, high amount of cycles so I could get enough material that I could just dilute it out and be quick to normalize. Um, so this is all sort of your experiment dependent. Once you set up the protocol, you could simply use the runtime parameters to adjust the amount of PCR cycles depending on what your input is, depending on what sort of how much extra sample you need if you plan to do like multiple enrichment captures. All this is easily changeable within the protocol itself. Here showing the post-enrichment yield. So the fragment size is nice for our sequencer. This is 14 cycles of amplification. This is 3.8 nanograms per microliter, which roughly calculates, I believe, to like 9 nanomolar, which you only need 4 nanomolar to sequencing. So this was enough for our uses. This was sequenced. This was put onto Illumina's base space and then analyzed using the Dragon Microbial Enrichment Plus, that sort of little app on their base or platform, and it's detecting 12 out of 12 SARS-CoV. In this particular case, it was kind of spiking on the larger side, 1 million copies of SARS-CoV. But in this case, I'm sort of sequencing for consistency across samples. I'm not trying to gauge how sensitive the whole platform is how consistent can I get every sample. And it's getting pretty much 100% coverage and just rough back of the math or calculations, it's about a 400-fold enrichment. So overall, it's a good start. I can make some user friendliness changes to the protocol, breaking up to sort of how I want to approach the throughput of sequencing, what kind of input I'm using, and sort of what depth am I looking for in sequencing.
Go for it.
Yeah, so that pretty much covers what I had to say, how I used both the Flex and all the additional sort of to me, all the additional toys and goodies that we added to the Flex, the stackers, the disposable PCR lids. Yeah, this was using, in my robot's case, it was using the low volume 96 channel head, especially because I was doing the enrichment capture, in which adding the panel, lowest volumes is like 2.5 microliters. Um, and again, it was sort of designing this protocol so to be as hands-off as possible, at least for me, so I could get it running and I just had to monitor it and check in during the QC and not have to worry about having to pause and have more labware. All right. And if you're ready, back to you.
Yes. Thank you, Matt. I'm going to steal that from you. We're going to do the old switcheroo here. Watch out for our mics. Thank you. Okay. Thank you so much, Matt. Always really cool to be able to kind of jump into the science that we are enabling here, as well as kind of the technology, right? The hardware and software that we are kind of continually working on to supply to the customer base in order to kind of be able to kind of work on these solutions. But as always, very interesting to see kind of like how much complexity you can actually start to accomplish on our systems. Okay, so as this is a live demo, we did have this running in the background here, and I just need to do a quick reset of it using our Flex touchscreen. In doing so, I'm going to start to run through some of the hardware that we have on the system as well. Okay, so first thing I'm actually going to do here so that we can actually see what's going on a little bit better is that we have a waste chute that's on the front of the instrument. This is typically kind of bolted into the sides. I'm actually going to kind of just remove this for today. We're going to be running a kind of more of a demo protocol, and so that is just kind of be running on a loop here. So we don't actually need to throw anything away in this protocol currently. So I can just take this off. Do not recommend for any actual end users to do this. There will typically be two screws that will hold this in place so that it does not move kind of during a protocol. However, in this case, we do not need it. So I'm just going to put this out of the way. Okay, fantastic. The next that I will be able to kind of talk through here are going to be the Flex stackers, kind of most specifically, as they were highlighted and as Matt kind of pointed out, some of the various points for them. Here for this protocol, we'll be using two stackers. Kind of difficult to tell in the camera angle. But what you can do is kind of add these on modularly. So you can have up to 4 stackers kind of equipped to a singular Flex instrument. With that, as kind of Matt had mentioned, currently we do kind of have a rule that it is best practice to have one type of labware kind of per stacker. And so for each stacker, you would have the ability to store tip racks As I'll show here, those tip racks can be lidded or unlidded, and using the flex gripper to then remove those lids if you have them on there. Uh, you have the ability to add up to 7 more tip racks. So that will be 6 within the tower itself, and then 1 on the deck. So if you wanted to add just tip racks, you can add 28 more to your protocol across 4 stackers. In terms of PCR plates, because of how they nest into each other, you can actually add up to 48 more PCR plates to the protocol. And then depending on deep well, you're kind of somewhere in the kind of like 16 to 20 range, depending on how they kind of stack into each other for the ability to have them exist within the stacker space. They have a very small footprint, as you can see. So they really only add about a kind of a foot of distance onto the bench space necessary. And so this means that you have the ability to kind of rapidly and kind of greatly increase your footprint in terms of how many labwares you have access to in one automated run, kind of without the need of greatly expanding the bench space that you need to have available to you. So this is kind of a fantastic add-on to the Flex system. Also, a quick note here, as with all of our modules, these are going to be compatible with any Flex that's out in the field, as well as with kind of like any combination of our modules. And so kind of the only kind of caveat there is if you wanted to have 4 of these, the plate reader that we also supply, the absorbance plate reader, also needs to exist on this right-hand side of the instrument, and therefore would not be able to kind of be run with all 4 stackers. But if you only have 2 or 3, you would still be able to run that. Also, as I kind of already had indicated here, we do also have a position that is compliant with the stacker in this frontmost position and the waste chute. So you still have the ability to do those. And if you are an end user who has the HEPA UV unit and are concerned about any of the UV, as these are kind of bolted onto the side of the instrument here, fear not. We have gone through and kind of made it so that there's actually a retrofit kit available for any Flex that's out in the field, which is going to allow for there to be connection points within the Flex windows that will identify when all of these stackers, as well as the front door, are all shut. So there is no chance that there is any sort of UV exposure. And if any of these doors on the Flex, such as these side doors or the connection points to the robot, are not kind of completed, the UV of the system will turn off. So always putting safety first. The second kind of new piece of hardware that I'm going to touch on here, as you can see back in the back of our robot right now, which will be moving soon, is the Flex 96-channel low-volume pipette. There are obvious benefits to using a 96-channel pipette to scale your throughput, and this one now supports kind of lower volumes as compared to our kind of previous pipette, as you could probably assume by me calling it the low-volume pipette. And this is kind of supported from volume from 1 to 200 microliters, which is ideal kind of for most NGS prep protocols kind of across the space. You can use this pipette, as Matt had mentioned, for single tip and single column pickup. So you can support all the different needs of this protocol with one pipette. There's really no need to have multiple pipette types to fulfill all of your protocol needs. As Matt had kind of mentioned, right, he's using different kind of reservoirs or tubes for his reagents. And so having the ability to utilize this kind of partial tip configuration element of the 96 channel is incredibly important for their protocol. One quick note on partial tip pickups is that you will not be able to use this kind of tip rack adapter that is needed for the 96 tip pickup to perform that function. So when the 96 tip rack adapter is in use, it actually provides extra force by pulling up on those And this force is not needed when you're using kind of fewer tips than 96. Okay, let me just confirm these offsets again. Okay, pressing go. The third thing that we have are also these new auto sealing plate lids, which you can see over here in the orange. Uh, these can be fully integrated into your automated protocol as they are compatible with the on-deck thermocycler and the flex gripper. These lids seal tightly once pressed down by the thermocycler lid, minimizing any contamination risk as you are cycling multiple times in a protocol. And very importantly, make sure that you don't lose any sample via evaporation during long protocols, such as the one that Matt had just shown off. A few other things that are on the deck here. In the back left, you can see our fully automated thermocycler. In this protocol, we'll be delivering a plate to it as well as a plate lid. You'll also see the magnetic block in the front here for any of your bead cleanups. I recently removed the waste chute to get it out of the way for demo purposes. But that is able to kind of throw away tips and plates as you're running protocols. Not on the deck, although mentioned in Matt's protocol, the temperature module, which can go from 4 to 95 degrees C, and a heater shaker module, which goes from ambient to 95 and shakes up to 3000 RPM. Okay, perfect. Now the protocol that's running kind of behind me now is not Matt's specific protocol as he was going through and running it, but instead kind of just showing off functionality of the equipment that we have available. So here you'll see the stackers dispensing 200 microliter tip racks. All of these currently have their lids on top of them. And so in protocol, you would just have to specify for these lids to be removed. You either have the ability to put those onto an empty tip rack or to throw them out through the trash chute. And then you can do the same thing with the tip racks themselves. Next, it's delivering kind of a variety of PCR plates. As Matt had mentioned, you could have reagents in these and put them in a specific order, or these could just be plates that are going to be used kind of like throughout the protocol and therefore just need to be kind of like retrieved and moved to the deck. Next, we're also going to drop off a plate at the magnetic module and then at the thermocycler. And then in this kind of demo protocol, we'll actually cycle to have this kind of have the same kind of end state as it started at. And so you'll see all of these kind of materials actually also returned to the stackers. So they have the ability to both retrieve and also store labware within them. As Matt had kind of mentioned, this is kind of unidirectional, so there is no kind of random access for these. So if you store a labware, it's kind of a last in, first out kind of situation here. So you might have to be strategic if you are hoping to kind of maximize your space with that. As you see while it's retrieving them, the kind of rightmost position, which is where the labware are kind of coming out from, is kind of called our column 4. This is only a gripper accessible position. So you can also use these positions just to store labware at. However, you will not be able to pipette to those positions. You'll have to use the gripper to move them. Now we're showing off the auto sealing lids here. So we won't be shutting the thermocycler or showing anything like that. You can use your imaginations. It's not the most exciting thing to demo. But here, there's a kind of a concavity to the, or a convex nature, apologies, to these plates, which allows them to kind of pop off of the PCR plate when they are not kind of in this pushed down mode. And so the thermocycler will actually, using these kind of notches here, provide some decent amount of force that is going to actually seal this lid to the PCR plate below it. Also, for anyone who is currently using our thermocycler, you will notice that the thermocycler that we are using here does not have one of the red seals. which are kind of used to help seal off plates. Not only are they not necessary because we're using these auto sealing lids, but they do actually cause a source of interference in kind of that pressing mechanism as you are doing this. Our PCR auto sealing lids have been tested kind of to ranges that actually exceed what the thermocycler temperature and also the heated lid are able to reach here. And we have data supporting kind of what are the evaporation rates and the yields shown with our kind of Opentrons tough PCR plates and the Opentrons tough auto sealing lids. As I had mentioned, this is now showing the ability to kind of store labware within the stackers here. You can also start with the stackers empty and store things into them. You do not have to kind of come in this kind of more cyclical nature that I am showing here for kind of demo purposes. And then here the thermocycler is performing an action which unsticks the plate from the base, which is kind of more relevant after you've done kind of repeated cycles with the plastic, but is kind of done by default on the protocol level. So we are super excited to be able to debut the stackers, as well as the auto sealing lids and the lower volume head. All of these are going to be included in the High-Throughput NGS Workstation. The lower volume head as kind of an option. You can still select the kind of higher volume or normal 96 channel head as well. And kind of as a full bundled solution, it is, really an enabling feature set to be able to give customers kind of as much walkaway time within our robot as possible. And kind of in that, I'll probably let this continue to run in the background as it kind of continues to loop, and now you can see it start to put back the tip racks. But I will also kick it over to Fran, who can start the moderation process if we have any questions coming in. And Matt, I'll invite you to come back over here with me, and I'll move this other camera out of the way. Woo!
Excellent.
Did it
Okay.
before you switched it. Too quick for you, huh?
Great. Thanks, guys. Great talk, great robot demo. So we have a couple of questions that have come in just before we start going through them. In case anyone isn't familiar, there is a Q&A box at the bottom of your screen. So you can just open that up and type your question in, and then we'll go through the questions that come in. Okay, so first question is from a Flex user at St. Jude. They have a 96 channel 1,000 microliter volume pipette, but no stacker setup yet. Question is, could you address how to reuse tips and perform sequential partial volume liquid dispensing in the protocol, i.e. aspirate large volume and dispense smaller volume to individual wells?
Yeah, so in our whether you are a Python or a kind of a protocol designer user, we have the ability to perform kind of like multi-dispenses, which is the action that you are talking about of aspirating a large volume and then kind of dispensing kind of smaller aliquots of that across a plate. Currently within Protocol Designer, you do not have the ability to do partial tip pickup to perform those actions. So you would have to do that either with kind of your full 96 channels. Those actions are entirely available within the Python API. And Protocol Designer is also catching up with feature sets such as partial tip pickup, which would also kind of complement the already existent features of multi-dispense to be able to kind of accomplish those goals.
Perfect, thank you. And thanks for that question, that's a great one. Okay, so the next question is also a great one. Do you get a reduction in pipetting CVs when using single tip pipetting or single column pipetting compared with a full 96 pickup?
Yeah, so another excellent question. So the actual mechanisms that we're using inside the pipetter the 96 channel specifically, is that we do kind of actuate all of the channels simultaneously. There's kind of a solid block within there, so that's moving all of the pipette channels up and down at the same kind of time. And so the actual mechanisms for pipetting are not going to be different with single versus multi kind of channel aspirations and dispenses. So the CVs should be the same across them. There might be some amount of like, kind of lower kind of mathematical ability to say that like if you aren't using all 96 channels, that there is less variability if you are only using one channel kind of like repeatedly. And so your precision and your accuracy may go up if you do just use one single channel, since you do not have to deal with any variation kind of across tips or anything like that. So there might be some kind of like small kind of benefits to CV and %D in that kind of mechanism. But overall, the actual mechanism of the aspiration and dispenses are going to stay the same, and any of those differences should kind of be accounted for by slightly less variation, as well as probably a smaller sample size.
I just speak anecdotally. I would see the most. I would normally see the most difference when doing like an ampere cleanup, but I've done like a short little sort of comparison, doing a full 96 full play to doing it with a single column versus doing it with a 96 channel. I think the main culprit, if you're doing it with a single column, is mostly the time difference delay between doing like the first column 1 to column 12. At least if I've been seeing like lower CV if I'm doing the 96 channel because it's processing everything simultaneously. What I did in that slight study was to do like the whole cleanup in batches of like 4 columns at a time to try and minimize the time difference, like the time between the first column and the last column. That's like the difference in evaporation of the ethanol. But so far, what I've seen is that the 96 channel is a little better in this, a little bit more even CV.
So also just to get it out there, if you were looking for the CV of your actual samples, Matt answered that question. If you were looking for pipetting CV more specifically, I answered that question. I could have been totally wrong, so hopefully Matt also got it. If not, you got a two for
Yeah, I know the samples, he knows the pipettes.
That's why we have both of you here. Great,
Same
thank you
concern.
guys. So going back to our original St. Jude user, so we already talked about this like multi-dispense action, but they have a good follow-up question as well. It's very good. So can you also do this kind of aspirate and then multi-dispense type action using the 96 channel, and a single tip or column pickup? Can you achieve this using Opentrons AI?
So you will be able to perform those functions with the Python API. I have not tested this with Opentrons AI. However, if it isn't a feature that is currently available to the AI tool, it is absolutely something that can be added in, and is something that it should have access to as it has been trained on our documentation. I do not know if that specific use case has been kind of more thoroughly tested.
Yeah, so maybe it's worth also explaining kind of how we build Opentrons AI. So of course, it's based on sort of an LLM model. So any sort of public documentation that Opentrons has put out, or any open product, publicly available protocol, is sort of fed into the tool. So you can theoretically anything that the robot can do, Opentrons AI can do, more or less. However, as Nick mentioned, there is we do spend some additional time really kind of stress testing particular functions and protocols to to really make sure that Opentrons AI has all the information it needs to be able to kind of perform that. So you should definitely be able to have a go at it, but I do not believe it is something that we have stress tested using Opentrons AI. that doesn't mean it won't be able to do it.
And if it does not currently work, definitely feel free to reach out to us. More than happy to help support that.
Excellent. Yeah, absolutely. We do really enjoy. There is, if you go to the Opentrons AI page on the website, I believe there is a form linked there for people to put their feedback in on the tool. And that can involve like requests.
And we take the feedback very seriously. So
yeah. Absolutely. So we don't have any more questions, but I will just give everyone like 30 more seconds in case someone is in the middle of typing something in furiously. I don't want to kind of cut you off. So if there are any more questions, feel free to add them into the Q&A box. We do have another 7 minutes if anyone has anything burning. Okay, there's nothing coming in. So I think you are okay to sign off, Nick and Matt.
perfect. Thank you so much for the help, Fran. Matt, thank you so much for going over your protocol. As always with these protocols, right, our science team has worked very diligently on how to get this to work. And here, even more specifically, right, if there are multiple 10-hour protocols, you can be rest assured that Matt has spent plenty of time with this one optimizing. Okay, great. Thank you so much, everybody. Have a good day. We'll see you next time. Bye.